What comes to your mind when you hear the word crystal? Is it something similar to any of the objects you see on the screen? If your answer is yes, we can start. Structural properties of materials are of significant importance. Structurally, materials can be crystalline or amorphous. Crystallinity is observed in material groups like metals or ceramics. In these materials, we see repeating units forming a long-range order, as a result, the crystal structure. On the other hand, when we look at the amorphous materials, we see them being generally glass or polymer materials, where the units are randomly distributed and as a result show short-range order. Although we briefly got familiar with the properties of crystalline and amorphous materials, one question is still hanging in the air. How do crystals form? As mentioned before, crystals show repeating units and long-range order. The ordered structures of crystalline materials form through the replication of the units via the symmetry operations, such as rotation, reflection, inversion, and translation. For rotation, 4 different cases are seen depending on the angle of rotation between each unit, namely 2-fold, 3-fold, 4-fold, and 6-fold. For an n-fold rotation, the structure rotates 360 divided by n degrees around the rotation axis and places a new unit same as the original one. So, in short, the larger the n value, the higher the symmetry is. If the repeating unit exists with the mirror image of itself with respect to a hypothetical mirror axis, then this type of symmetry is called as reflection. For inversion, an inverted form of the repeating unit is produced through the center of inversion. And lastly, in translation, the repeating units are placed side by side in three-dimensional space. Using these symmetry operations, 7 different crystal systems were developed, and these crystal systems are cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and lastly, triclinic. The dimensional and the angular variation leads to the difference between these crystal structures. Let's take a look at them. For cubic, A, B, and C dimensions are equal to each other. The angle between B and C is labeled as alpha. The angle between A and C is labeled as beta. And the angle between A and B is labeled as gamma. And these angles are equal to each other and 90 degrees. For tetragonal, A and B are equal to each other and not equal to C. Alpha, beta, and gamma are equal to each other and 90 degrees. For orthorhombic structure, A, B, and C are not equal to each other, and alpha, beta, and gamma are equal to each other and 90 degrees. For hexagonal structure, as the name suggests, base and top planes are in shape of hexagons, and the structure is in the shape of hexagonal prism. In this crystal system, A and B are equal to each other and not equal to C. Alpha and beta are equal to each other and 90 degrees, and gamma is equal to 120 degrees. In rhombohedral structure, A, B, and C values are equal to each other. Also, alpha, beta, and gamma values are equal to each other as well, but these angles are not equal to 90 degrees. For monoclinic system, A, B, and C are not equal to each other. Alpha and gamma are equal to each other and 90 degrees, and beta is not equal to 90 degrees. In triclinic structure, A, B, and C are not equal to each other. Also, alpha, beta, and gamma are not equal to each other or not equal to 90 degrees. Further manipulation of these crystal structures have led up to 4 different variations of each of these crystal systems. Let's take a look at them. Up until now, the crystal systems that we have investigated had the simple structures. In simple structures, 8 atoms are placed at the 8 corners of the cell, and 1/8 of each atom is inside the cell. Let's take a look at the simple structure in 3-dimensional space. The next structure is the body-centered structure. Similar to the simple structures, body-centered structures have 1/8 of each of the 8 atoms at 8 corners, and in addition to them, there is one atom placed in the volumetric center of the cell. The atom in the center is where the body-centered structure name comes from. Let us take a look at the body-centered structure in three-dimensional space. The third structure is the base-centered structure. In addition to the 8 atoms at 8 corners, this time there is one atom placed to the center of the base surface and one atom placed to the center of the top surface of the structure. And half of each of these atoms are inside the volume of the base-centered structure. Let's see how base-centered structure in three-dimensional space looks. The fourth and the last structure is the face-centered structure. In addition to the 8 atoms at the corners and 2 atoms at the centers of the base and top surfaces, now there are one atom placed at the center of the right surface, one atom placed at the center of the left surface, one atom placed at the center of the front surface, and lastly, one atom placed at the center of the back surface. So, in short, face-centered structures have 8 atoms at 8 corners and 1/8 of each of these atoms are inside the cell. In addition to them, there are 6 atoms placed at the centers of the 6 surfaces and half of each of these atoms are inside the cell. By using these 4 different structures and previously shown 7 different crystal systems, Bravais lattices were developed. And after eliminating the repetitive lattices, 14 different Bravais lattices in total for cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and lastly triclinic systems are defined. Now let's take a look at these Bravais lattices. For cubic lattices, we have simple cubic, body-centered cubic, and face-centered cubic structures. When we look at the tetragonal structure, we have simple tetragonal and body-centered tetragonal Bravais lattices. Orthorhombic crystal structure is a special case since it shows all 4 alternative cases. So there are simple, body-centered, base-centered, and face-centered orthorhombic Bravais lattices. And unlike orthorhombic Bravais lattices, hexagonal structure only shows the simple hexagonal Bravais lattice. And same as in hexagonal structure, in rhombohedral, we only see simple rhombohedral structure. For monoclinic, there are 2 different Bravais lattices, which are simple and base-centered monoclinic lattices. And lastly, for triclinic, there is only simple triclinic Bravais lattice. As we are done with defining the Bravais lattices, now we reach the end of this video. In the next video, we will keep talking about the crystal systems, and we will cover unit cells and crystallographic points, directions, and planes. Until next time.